It is a pleasure for me to welcome Emily Jensen here today. Emily is an assistant professor in the EC Electrical Computer and Energy Engineering Department at University of Colorado Boulder. She has an affiliate appointment in the robotics program. She did a couple of postdocs before that at Northeastern and UC Berkeley, where she collaborated closely with industry experts at Siemens. She has a master's and PhD in electrical and computer engineering from UC Santa Barbara and a BS in engineering mathematics from UC Berkeley. She's received a couple of awards, including the UC Regents Graduate Fellowship, as well as the Amelia Earhart Fellowship for Women in Aerospace Engineering. So with that, welcome Emily here, and we look forward to her talk.
Thank you for the introduction, and thanks everyone for inviting me here. I'm really excited to share some of my research with you today. Today I'm going to talk broadly about optimal co-design of spatially distributed systems and controllers. I'm going to do more breadth than depth, and happy to answer questions after my talk or offline if you'd like me to go into more detail about any of these projects. Okay, so let's get started. So what is motivating me to study this? So I'd argue that engineering systems today are becoming increasingly complex, and I think we can all agree on that. Some examples is we're seeing robotic systems move from rigid systems to more flexible systems with more degrees of freedom, perhaps more actuation, more sensing. Another relevant example is the power network, which we're seeing become increasingly complex as we move from synchronous generators to inverter-based resources. So our future power network will have these green nodes that represent inverter-based resources or renewables. And as these engineering systems become more complex, we see new opportunities arise for both control of these systems and design of these systems. Some aspects of these new systems I'd like to highlight is multiple timescales arise. I've mentioned already that we see increased sensing and actuation in these systems. And as we see more parameters or more flexibility, we have more opportunities for design. So we have a larger design space that we can work within. And within this context, I claim that a framework is really needed for a few things. First, for scalable controller design. So if I have really immense sensing and immense actuation, if I want to implement a controller in real time, I need to make sure that my controller scales as the amount of sensors and amounts of actuators increase. And if my design space become larger and larger, I need to have a framework to make intelligent design choices, right? It's less obvious how to do these designs ad hoc as I have more knobs that I can tune. And just to dive a little bit deeper into this framework that I think is needed, for scalable controller design choices, here I'm highlighting a controller that contains two blocks, one gain representing a state estimator and one gain representing a state feedback controller. And I'll go into this block diagram in more detail later in the talk. But my claim is that for this controller to be scalable, I really need these gains or these matrices to be represented by sparse systems, right? Sparse matrices, so that I can compute this matrix vector computation in a parallel manner over distributed computing units. And for intelligent design choices, I'll bring up kind of a classical example. So perhaps you've heard of this before in the context of co-design. It's much easier to steer a bicycle with the handlebars up front where they are. If I were to move the steering to the back of the bike, no matter how good I am as a cyclist, I will do worse, right? So this kind of idea that how I design my system limits how good my controller can be. Okay, so that's the framework I'm going to be talking about today. And like I said, I'm going to go for more breadth than depth. So part one of this talk, I'll discuss how we can link system design choices to controller design through a collection of different case studies. And I think this highlights the diversity of this approach. So I'll look at the impacts of incorporating grid forming resources into wide area control design for power networks. I'll look at design and control trade-offs for a soft-bodied robot. And then I'll talk more theoretically about LQG control of the wave equation. In part two, I'll talk about challenges in scalable controller design and some recent advancements that my group has made there. Okay, so let's start with part one, really looking at this question of how does design of my system impact my achievable control? And I'll start with the first case study on the impact of incorporating grid forming resources into our power networks. And with all of this work, I really want to thank my students and my collaborators who've done a large portion of the work that I'll present today. Okay, so I mentioned at the beginning of this talk that moving forward, we anticipate our power network changing in terms of its topology and its dynamics. So in the past, everything has been driven by these large synchronous generators, these massive power plants. Moving forward, though, as we incorporate more and more renewable sources of energy, be that wind or solar, all of these resources are connected to our grid through inverters. And our future power networks will have larger and larger shares of these. So these resources that are connected to the grid through inverters are called inverter-based resources, or IBRs, and we'll largely categorize these resources by the control policy that governs their dynamics. Two broad categories for such control policies are grid following and grid forming. Grid following is more common right now, but a little bit more boring. Essentially, they just match the frequency that they see in the grid and try to copy that via a phase locked loop. Perhaps more interesting and more important moving forward are grid forming resources, which use some control policy, this is typically a droop control, to create a desired voltage output in response to frequency changes that they detect in the network. And as we move forward, grids that have higher shares of inverter-based resources or only inverter-based resources will require grid forming inverters to form the network because grid following need a frequency to follow onto. Okay. So why is this a challenge? We have extensive data and simulations already for synchronous generator dominated grids. That's what exists today. So we have all of this data about how they're working. We have really intensive models to understand these systems. But we lack understanding of how grids dominated by grid forming resources will behave. These don't exist yet, so we can't just study them heuristically. And models that are simple and easy to understand are really lacking. An additional challenge of incorporating more grid forming resources into our power network is that these grid forming resources introduce additional measurement signals and additional forms for potential actuation. So rather than having one synchronous generator, I guess we can zoom in like one of these nodes, I'm replacing one synchronous generator with a whole cluster of grid forming resources. And with that replacement, I'm incorporating many, many more measurements I might need to track to get an accurate understanding of where my system is. And why this is challenging is because if I want my control policy, my wide area controller, to sense what's going on in my network and actuate in real time, I now have much more data I need to process in real time. And as that amount of data grows, I run into an issue of, can I do this quickly enough? I really need this to be distributed for that to be possible. Okay, so the question I want to ask in this case study is how do grid forming inverter dominated design choices impact metrics that will help us design wide area controllers for these new power networks? For instance, should wide area controllers in these new regimes actuate only at synchronous generators, which is what we're doing now? Or should I also leverage my grid forming resources for actuation? What measurements are important? If I have many, many more measurements, do I actually need to use all of these to achieve good control, or can I do good enough by just using a subset? And my goal is to leverage really simple models of grid forming resource dynamics to obtain interpretable answers to questions like these. Okay. So in order to answer this question, the simple model I'm going to choose is a two-state model that accurately captures the dynamics of a grid forming resource resource that's governed by droop control. So this model comes out of the paper referenced at the bottom. That's pretty recent. And what's nice is that we see that although the system is linear, time invariant, and only has two states, the dynamics pretty accurately capture a 17-state model of these resources. Not perfectly, but we're planning to do feedback control, so our model doesn't have to be exact. And when we simulate the IEEE 39 bus system with either synchronous generators at each node or grid forming resources modeled by these simple dynamics at each node, we see vastly different responses. So these plots are showing the frequency of each synchronous generator on the left and each grid forming resource on the right when I hit the system with a load step at one of the buses in the network. And in particular, note the difference in the time scale on these figures. So what we see is the response with our grid forming resources is much quicker and appears more localized. So really only the generators near the step response are seeing a massive reaction. In contrast, the synchronous generators tend to move together synchronously so that the whole network responds to this disturbance. And again, this hints to this question of, now that we have these very novel dynamics, how can we use this information to more intelligently design wide area controllers? There's a lot of ways we could approach this question. We're examining this from a number of metrics. I'm going to just highlight one of those today, but happy to chat about others offline. And this is a metric of controllability. So what I'll demonstrate is that we can select the parameters that describe our grid forming resources to determine the required control effort of a wide area controller. So to start, I'm going to begin with a very simple setting. I'm going to consider a network with just 3 nodes, each of which is a grid forming resource, all of which are identical, and the coupling between these 3 nodes is also identical. You can view this network as a Cron reduction of an idealized IEEE 9 bus network, where the effective admittance in each line is a constant number B. A few more parameters are in my model of my grid forming resource represents the grid forming droop coefficient. I likely can't control this very much because my droop coefficient ensures equal power sharing among the network, so I don't really want to mess with this. Likewise, my effective admittance B is determined by my network structure. This is pretty fixed. I can change something though. I can change this parameter TC, which shows up in my block diagram. And this represents a time constant of the grid forming resources power measurement filter. And I can kind of select this to be what I want it to be. Okay, and I can view the ratio of TC to R as something like an inertia in a synchronous generator. And I can view the ratio 1 over R as something like a damping in a typical synchronous generator. If I write out the state space model for this 3-node network in terms of a state, which includes deviation in frequencies at each of my nodes, and deviation of frequency from my desired 60 Hertz at each of these nodes, I have a linear model x dot is equal to ax plus bu, where u is my power change that I'm controlling. And we see that my A and B matrices depend on the parameters B, M, which I can control, and D. So what's interesting is that for this system, I can analytically compute the eigenvalues of my controllability gradient. And these eigenvalues are determined by these parameters. Recall that we said that M is really the only parameter that I'm able to tune to whatever I want. And this shows up in one of my eigenvalues with multiplicity 3. And just as a reminder what the controllability gradient is, so I can visualize its impact by drawing an ellipsoid. The axes of this ellipsoid are the eigenvectors of my controllability gradient, and the length of those axes are the corresponding square root of the eigenvalues. And everything in this ellipsoid depicts a point in my state space that I can control to the origin with energy 1. Right, so it's telling me how easy or difficult different directions in my state space are to drive to the origin. So what I'm seeing is that a larger eigenvalue represents a direction that's easier to drive to the origin with less effort. And thus, if I can choose m to be smaller, I'll require less control effort to move in that direction. Of course, that's a really simple example. I only have 3 nodes. Power networks are huge. So let's make things slightly more complex. I'm going to move up to a network of n grid-forming resources, but I'm going to keep things spatially invariant. So everything's in a ring, and all of the grid-forming resources are identical, and all the couplings are identical. Don't worry, we'll get more complicated soon. But again, I can solve for the eigenvalues of the controllability gradient analytically. And they take the same form as for the 3 node case. So again, only one of these depends on my effective inertia m, which is the parameter that I can control. And interestingly, one of them now depends on the size of my network. Okay. And if we examine the corresponding eigenvectors of these eigenvalues, we see that the first 2 eigenvalues correspond to eigenvectors that only modify relative angles, whereas my eigenvalue that depends on my effective inertia that I can tune and has multiplicity n, where n is the number of nodes in the network, corresponds to eigenvectors that move along frequency directions. So what I'm saying is it's easier for me to modify frequencies, or requires less control effort, if I can make m larger. Yeah, make m smaller, and thus make this ratio larger. So again, very idealized, but nice because we have these interpretable analytical results. It's always nice to verify these really clean results with more complex settings though, right? So now we look at the IEEE 39 bus system. Again, all grid forming resources at my 10 generator nodes. But I'm now gonna allow for asymmetry in my couplings, right? So I'm using the effective admittance of the true IEEE 39 bus system. And what I'm plotting here is, oops, I'm just gonna show this again. So I'm plotting the eigenvalue that depends on my effective inertia on the top. And remember that eigenvalue has multiplicity depending on my network size. So there's many of these eigenvalues, but they're actually all just right on top of each other. And I see that the value of this eigenvalue scales with my effective inertia. Okay. In contrast, all of my eigenvalues that correspond to eigenvectors that don't align with frequency directions in my state space are independent of my effective inertia. So this trend holds for more complex systems as well. Let's make things, oh, I did want to say something. So my claim is this kind of suggests that we should explore how to actuate at grid forming resources when we design wide area controllers in the future. And in particular, we should choose our local grid forming strategies to have potentially low values of effective inertia to make wide area control more effective. Of course, we should consider other implications of these design choices. Typically, we don't gain something good for free. So we're currently trying to see what trade-offs might exist in this space. Okay, I'm gonna take it one step further and look at a heterogeneous network. So everything I've been looking at so far assumes that every single node in the network has been replaced with a grid forming resource. Here, I'm assuming that I keep some synchronous generators. So within my IEEE 39 bus system, I replaced 3 of my generators with grid forming resources. And thus I reform my dynamics. So I have a new dynamical system. X dot is AX plus BEU, where my A and B matrices have changed because I now have heterogeneous dynamics that correspond to both synchronous generators and grid forming resources. And I think about modifying my B matrix so that I can actuate either at only synchronous generator nodes, only grid forming resource nodes, or both. And then I compute the corresponding eigenvalues of my controllability gradient. And what's quite surprising is that I don't notice very much difference in magnitude of my eigenvalues between full actuation at every node, versus actuation only at my grid forming resources. In contrast, if I only actuate at my synchronous generators, my eigenvalues are much smaller. So we see that most of our controllability comes from our grid forming resources. And I do want to acknowledge the shortcoming of this result is I'm assuming I can actuate at all my grid forming resources. Of course, I need to have some available headroom. So this is a bit oversimplifying things, but I think still nicely points out that we should think going forward when designing wide area controllers, how we can leverage these new technologies for effective control. Okay, so that wraps up case study 1.
Just a quick
Yeah, go for it.
So if now we're given like a power network, in Arizona, let's say, right?
Uh-huh.
And you know the number of the nodes that potentially you could place, this type of actuator, if I understand it correctly.
Uh-huh.
Then what would be the design or optimization process to do the placement? It's some type of actuator placement given the Gramian, but I suspect maybe the Gramian, I'm not sure if you have a closed formula. Maybe you have. I'm outside of this.
Yeah.
Just I'm curious. Yeah. Could you give me an intuition?
So we haven't thought much about placement here. We kind of just picked arbitrary locations to put the grid forming resources within the 10 nodes. And we saw similar trends regardless of where we selected. But again, this is just kind of one case study. So the question of where to place these, I think, is still open. And I am not claiming that this will hold for every network, but yeah.
No, myself also, I wasn't wondering, about the claim. Just I was trying to understand, in terms of some also works in the past on Gramian driven, I think, actuator placement, but I'm not sure if they apply directly as is. But thank you. This answers the question. I could follow up later. Thank you so much.
Okay. And then, just to clarify, the analytical expressions for the eigenvalues, we could only obtain for a homogeneous network. So with the heterogeneity here, we really could only compute these numerically.
So you need the data-driven approach. I think this answers the question. Thank you so much.
Yeah, no problem. Any other questions before I move on? Yeah, Jeff.
So, obviously your Gramian results, for your linearized system, these are small.
Yes.
Is there any kind of is part of the trade-off here what happens to the dynamics when dynamics are large and the eigenvalues? Because you want the eigenvalues to be, to be big. But do you pay a price by like shrinking the domain of retraction or anything like that? Is there anything that happens in the nonlinear setting that's interesting there?
That's a great question. So I would say we're definitely assuming we're operating within the linear regime, which is, I think, typical for wide area control design and power networks. Of course, this should be followed up by a full nonlinear simulation study. And like I said, I do think this is coming at the expense of something. It's unclear what yet. But I think it brings up an important question of here's one direction you can move in. If I'm benefiting myself in this direction, am I losing something somewhere else? I think we must be, but yeah. Any other questions? Okay, moving on, just to kind of drive home my point that we can design systems to impact resulting controllers. I'm going to look at a second case study. So this looks at system design and control trade-offs for a soft-bodied robot. My student Andy did most of this work, but I also collaborated with Professor Cody Scarborough, who did his PhD here. So wanted to give a shout out to him. Okay, so here we're looking at a model of a soft-bodied robot, so kind of like a worm that's inching along. And we're modeling the dynamics as a nonlinear wave equation where my nonlinearity comes from my friction force, which is a function of my du dt. And we're modeling this nonlinearity by this asymmetric curve. So the red curve is symmetric, and we're shifting the curve up by a parameter NF to obtain the blue curve that models our friction. And the reason for this asymmetry is that I want preferential direction of movement of my crawler. So if friction was symmetric, my crawler would just kind of like contract and expand and never move, right? I need asymmetric friction to kind of like preferentially drag one way or the other. Okay, so I'm going to focus in on two parameters here, NF, the asymmetry, and my friction force, which I can assume is kind of dictated by design. So I'm going to design the body of the crawler to have this preferential direction of motion. So perhaps in the design process, I can change NF. And then rho is the density of my crawler. So perhaps I can change this as well. And I don't fabricate these robots, but it does seem like they're pretty efficient methods for fabrication. So perhaps not so crazy to think that we have some flexibility in designing these parameters. Okay, so what we did here is so this is a nonlinear wave equation. The friction force is non-smooth and asymmetric. So seems maybe like we can't get an analytic solution to this, but we actually got something quite close. So we used perturbation analysis and leveraged multiple timescales in the system to obtain an analytical solution to a reduced order model that seems to pretty accurately capture the full dynamics. So blue is the analytical solution to our reduced order model, and red is a numerical solution to the full dynamics. So we can see a little bit of mismatch, but overall our analytical solution does quite well. And why the analytical solution is nice is because it points to parameters that we can leverage for design, right? I want to understand how parameters are affecting my design choices and affecting my control. And I can't do that as well with just a numerical solution. Okay, so leveraging that analytical solution to the dynamics of my system, we're able to obtain a maximal attainable velocity of my crawler. So the maximal attainable velocity of my crawler, V star, I'm saying approximate because this is according to my analytical solution, but of course we've seen that's very close to my true solution. And this depends on my parameters that I think I can design, NF and rho. This parameter CD here is just rho times my gravitational constant. And so I can see that by effectively selecting these parameters, I can modify the achievable velocity of my system. And now how this ties into control design, I'm going to highlight here a trade-off. So what we see is that increasing my velocity doesn't come for free. So my control, so my control policy depends on three things: so frequency of oscillation, a wave number of oscillation, and a forcing strength. So the three horizontal axes determine the three choices in my controller. And I'm plotting here the corresponding velocity of my crawler, mileage, how far I can go, and stress, according to like how much stress I'm putting by contraction and expansion. And so what I see is that actually velocity and mileage there's a complete trade-off, right? So if I increase my velocity, I actually decrease my mileage, right? So this is kind of highlighting like, okay, I can choose these parameters to get a higher potential velocity, but then when I hit that higher velocity, I move less far with the same amount of energy, right? So this is mileage for a given energy. And so I think this again highlights this idea that we can look at control and design of a system together to make choices based on what we want to achieve. Do we really want to achieve maximal velocity, even if it's at the expense of mileage, or should I explore this trade-off space more generally? Okay, any questions there before I move on to my next case study? Okay, so this is a little bit more theoretical. So here we're really focusing on how design decisions affect the structure of optimal controllers. We're going to focus here on the wave equation and examine how the wave speed dictates the locality of an LQG controller. So really the bigger picture question I'm asking here is, do system parameter selections impact the locality of an optimal controller? So we're going to consider wave-like dynamics. So here's my wave equation, which depends on both a spatial coordinate and a temporal coordinate now. I'm going to assume continuous time, infinite horizon, and I'm going to assume that my dynamics are evolving on an interval with periodic boundary conditions. My parameters here are my damping and my wave speed. Applications of a damped wave equation are vast, but include the soft-bodied crawler that we just saw, transmission lines, and many more. And spatial discretizations of the wave equation describe coupled second-order system dynamics like a vehicular platoon or synchronous generators in a power network. Okay, so we can think about many different control policies here. I'm just going to view classical LQG control. So as you might remember from your controls class, the optimal LQG controller is built according to the separation principle from a static state feedback gain, that's the solution to the LQR problem, and an optimal state estimator or Kalman filter with gain L. The dynamics of my system, the wave equation, I'd say are completely localized, right? I have spatial derivatives. Basically, the dynamics at one point depend on neighbors really close by due to the spatial derivative. So my dynamics are really local. So the structure of the controller overall, which depends on a copy of my state dynamics, my control gain K and my estimator gain L, is really determined by the locality of these gains, the matrices K and L. Okay. To simplify my exposition of results, I'm just going to look at the control or LQR gain K. Remember that the full LQG controller will follow from separation principle and duality. So L, same process. Okay, so if I just zoom in on the gain K, I can view this as mapping my state estimate to my control signal. So a vector of state estimates to a vector of control signals. And I can think about what it means for this controller to have a certain degree of locality. So let's think about three different cases. The least local case corresponds to a centralized control policy when actuation at each of my spatial coordinates depends on a weighted sum of all of my state estimates. So this looks like a full matrix, right? So to compute all of my control signals based on my state estimates, I multiply my state estimates by a matrix which probably has no zero entries. Okay, in the full continuum setting, if I'm not discretizing things, I'm assuming I can actuate continuously and estimate continuously. This matrix vector multiplication becomes an integral, right? I'm integrating against every single point on the body of this crawler to actuate along every single point in this continuous domain. Okay, so here I'm assuming I have one central computing unit that instantly accesses all my state estimates and computes all my control signals in real time. Contrast this to kind of the complete opposite, a decentralized control policy, in which actuation at a given spatial site depends only on the state estimate at that exact site. So what this looks like is my actuation at spatial location x sub j is just a constant number kj multiplied by my state estimate at the same spatial site x sub j. If I look at this over a vector of different spatial sites, this looks like a diagonal matrix. So I apply my diagonal matrix, multiply it to my vector of state estimates to obtain my vector of actuation signals. And clearly I can see that I can compute kind of each of these actuation signals at a different computing unit, right? I could compute each row of this matrix vector multiplication at a different computing unit in parallel if I wanted to. So this is purely local. I'm only using my own information to compute my own actuation signal. We can think about something in between, which I'll refer to as localized, and say that my actuation at a given spatial site depends on a local subset of state estimates. So this looks like multiplication by a sparse matrix, not diagonal, but not full. And again, this looks like if I'm approximating everything with a continuum, an integration where my bounds of integration are over some compact region around my point of interest. Okay, and again, in this case, I can distribute my computations across multiple computing units, each doing some portion of this matrix vector multiplication. Okay, so now that we've discussed what locality is, the question is, how do the parameters of my system affect the locality of my controller? Remember, my parameters are my damping and my wave speed. So the first thing I'm going to do is technical math here, but don't worry, I think you'll still get the end result even if you want to ignore the math. I'm going to formulate this for those who are interested as an abstract differential equation. So I'm going to write this to look like x dot is ax plus bu. But remember, my state here is really a function over my domain, my interval, right? So my state is actually infinite dimensional. But I can write this to look like x dot equals ax plus bu, and I'm going to use extensions of finite dimensional linear systems analysis. Okay, and just as in finite dimensional linear systems, there's something like a matrix exponential e to the at, which tells me how I evolve from an initial condition to a state t steps future in time. Rather than a matrix exponential, this is now something called a C0 semigroup, which is generated over a Sobolev space. And this Sobolev space has a norm which is equal to L2 norm of my first component, or sorry, L2 norm of my second component. My first component is weighted according to its L2 norm or energy, and then the energy of its spatial derivative. So I can kind of think of this as weighting a kinetic energy of my second component and a potential energy in my first component. Okay. So with this framework, I'm able to rigorously formulate the LQR problem in infinite dimensions. So this looks just like my standard LQR problem, which is X transpose QX, right? Now this X transpose QX is just replaced with an inner product over my Sobolev space. And similarly, I still have my control energy weighted by this parameter R and subject to my dynamics. Okay, so, well, I kind of wanted that to highlight the R and not the plus, but highlighting the parameters that we can modify. I can modify R, the weight on my control effort. Q, I'm thinking this is the weight on my kinetic energy. And then alpha down here, I'm thinking of as the weight on my potential energy. Okay, so here's our result. We've shown that the solution to this LQR problem, right? I'm not putting any constraints. I'm just solving the pure LQR problem. The solution to this is completely decentralized. If and only if I select my parameters according to this ratio. Okay. And all of my pictures talked about decentralization in terms of a diagonal matrix. Here, everything is continuous. So what I mean by completely decentralized is that I'm convolving my state estimates with a kernel that's described by a Dirac delta distribution, right? So I'm just convolving my state estimates with a delta in space. So really my actuation signal at a given site depends only on my state estimate at that site. So what I'm saying is I actually gain nothing from looking to my neighbor. The best I can do is just use my own local information. So essentially we can tune our system by selecting our wave speed C appropriately. For the crawler, you could think about this as tuning the elasticity of the material. Interestingly, decentralization is completely independent of my damping. The result also holds if instead of having periodic boundary conditions, I implement homogeneous Neumann boundary conditions. And like I said, the extension to full LQG follows just from separation principle and duality. So I think this is very interesting and non-intuitive that for certain values of wave speed, my optimal LQR controller tells me only care about what's happening right here. Don't care about what's happening even sort of to the left or right of you. And that's quite unintuitive. So I just want to briefly discuss the tools we used in the proof. So first we simplified our computations by non-dimensionalizing everything. Then we leveraged a theorem by Curtin and Zwart that tells us the optimal LQR control policy, just like in finite dimensions, can be obtained by solving a Riccati equation. Now this Riccati equation is operator valued rather than matrix valued. And we leveraged Fourier analysis to get an analytic solution. Okay, so let's dive deeper because of course this should raise some concerns. The first question would be, well, how robust is this result? So what happens when this exact wave speed is not selected? You would hope that if your wave speed is close to this, your controller would still be close to decentralized, right? Because you can't pick a number exactly. Okay, so what we see here is that if I perturb my wave speed slightly, the controller that's optimal still has what I'll call limited connectivity. So what I mean by that is we can see that the optimal control kernel, so I'm going to convolve this with my state estimate at any time, this decays. So I have this exponential decay, and it decays more rapidly if I'm closer to my optimal wave speed. And using small gain arguments, we can show that truncating this gain doesn't degrade performance too much. So I can kind of truncate as much as I want, get really, really close to something completely decentralized and still do okay. And this extends to discretized dynamics. So you might say, okay, well, in practice, everything is discrete. I agree. So let's discretize our dynamics. This is the discretized wave equation, where this bold-faced letter D represents a discretization of the derivative operator, so a matrix of 2s and -1s. If we look at the LQG problem here, assuming some covariance of my noise and disturbance, and design a controller to minimize this LQG objective, where notice here R is the weight of my control effort. This is my Q matrix and my LQR cost. So weights here include a weight on potential energy, again, kinetic energy and control effort. Again, we see that for certain parameter choices, the matrices and my optimal LQG controller are actually diagonal gains. Right, so I didn't impose any constraints. I just solved the Riccati equations and my matrices turned out to be diagonal. And so again, quite surprising that if I just choose my wave speed the right way, my optimal controller is completely decentralized. I don't do better by sharing information.
Why is that with a capital W? Why?
Great question. I think we don't know is the short answer. So if anyone wants to help me gain intuition.
Maybe can I ask a maybe a relevant question?
Mm-hmm.
Right? So if you have the full decentralization, is the actual performance in terms of tracking, right? I mean, myself, I'm thinking in terms of mobile robotics always, I mean, you have like your quadrotor and I have a reference trajectory. I want to track this trajectory, right? So now I have full decentralization. Can I actually do good tracking, or essentially I pick the parameters in a way that it ruins up my tracking, but it happens that these matrices, they become diagonal, but at the end my performance is not good anymore.
Yeah, so that's a totally valid question. The question is basically like, do I not share information because I'm going to do terrible no matter what? Don't even try. So of course we looked at that. And the answer is no, there's not a complete trade-off. So you were a plant in the audience for this slide. So what we did here is we plotted, so the black curve represents parameter values for which my controller is completely decentralized. So if I just go back, right, my parameters here, Q1, Q2, alpha, C, my wave speed, and R. So there's a whole range of values for which I'm completely decentralized. So we're plotting a black curve in a parameter space that captures a bunch of those points. And then the colors correspond to the corresponding LQR cost. So what we see is we can actually move along this curve of complete decentralization and vary the performance that I get. So it's not that there's a complete trade-off. Does that answer your question?
I'm trying to think in the sense that this is the total cost, right? Which
Mhm.
includes both how the control behave in terms of energy, but also how the state behave.
Yes.
And yeah, I'm wondering what's the trade-off also between, not, yeah, the trade-off, essentially, if I will not sum these two, but they're independent, right?
Mm-hmm.
How much accuracy I have,
Yes.
independently of how good is my controller,
Yes, I understand.
or how much is the energy of the controller.
Yeah. So I didn't include these plots in the talk, but we did look at these. So essentially looking at like just this cost and just each component of this cost. And again, we didn't see any complete trade-off there. We're really curious to understand why this is happening. We spent a lot of time trying to think about this in terms of like kinetic energy and potential energy and like elastic materials. And this is work in progress. So if anyone has the answer or wants to chat, we're very curious for a physical explanation.
Yeah, no, it's very nice, yeah.
Okay. And then similarly, a robustness result holds. So if I don't exactly hit my parameters that give me complete decentralization, my optimal gains are still close to local. So they look essentially like these matrices where darker colored squares represent higher values, lighter color squares represent smaller values. And again, we can kind of use small gain arguments to zero out some of the small values and not degrade performance too much. This is interesting, so I thought I'd throw it in there. What I kind of glossed over is that my Q matrix looks like my Sobolev norm. So it looks like it has this spatial derivative in it. It's really a discretization of a spatial derivative. If I didn't have that there, if I just replace this with Q1, so I'm not weighting something like a spatial derivative at all, my gains are always full. There's never any sort of localization or decay. And so this is pretty interesting. It almost kind of hints at this idea that the PDE or the continuum limit kind of informs control design for the discrete system. And again, quite interesting, right? I guess our intuition here is that as you discretize more and more finely, you start to look like a PDE. And in the PDE setting, the problem on the right is not well posed. So this becomes a non-well posed LQG problem. You can't solve it. Whereas the problem on the left-hand side is well posed. Again, in finite dimensional land, both are fine. But it's just an interesting point that we found. And again, we don't have a physical explanation as to why, but we think it's interesting and are trying to understand whether this holds more generally for PDEs formulated over Sobolev spaces and their spatial discretizations. Okay, so that concludes part 1 of my talk. Part 2 is really, really short, don't worry. Is there any questions there? Yeah.
Exactly. So what conditions of like the initial state matrix like A and B?
Oh, yeah.
You like get this bound like is optimal when the K is diagonal.
So for initial condition, if I'm understanding your question correctly, the cost depends on my initial condition, but the optimal gains are independent of initial condition. For the discrete setting, for the continuum setting, I do have to ensure that my initial condition is in the domain of my operator. So like it's weakly differentiable and stays in L2. Is that your question?
Yeah.
Other questions before I move on? Okay. So I talked a lot about design. And I think realistic criticism is, okay, well, as a controls engineer, you probably aren't designing all these systems. You're probably given a system and asked to design a controller. So the second part is just to briefly tell you that I do think about that question too. And I think there's a lot of challenges in designing controllers scalably when we're given a really large scale system. And I'm going to just briefly touch on some of the current work I'm doing on this in my group. Okay, so to talk about this, I first need to generalize my definition of a local controller. Everything I've talked about has been in terms of static matrices, right? I've just talked about a matrix as being diagonal, sparse, or full. But let's think about what happens for a general dynamic controller. Okay, for a static controller, its sparsity structure I can think of by just looking at how each actuation signal depends on each measurement in the network, right? So here I'm looking at these drones. This is a topology that interconnects, or like some graph structure that interconnects a local subcontroller at each drone. And so my actuation at drone 2 can only depend on the measurements that it can access according to this graph, right? So it can access, I feel like this doesn't match my picture. Oh yeah, it does. Okay. So it can access measurements 1, 2, and 3, right? 1, 2, and 3 are connected, and it can't access measurements 4 and 5, so those gains have to be 0. Okay, and I can fill in and look at how each actuation signal must look, right? It can't depend on measurements it doesn't have access to. And I can condense this all into a sparse matrix that represents my controller gain. Okay, let's make this slightly more complex though, and think about dynamics. So even without a direct connection in this graph topology, a node might be able to be reached indirectly through an intermediate connection. So for instance, nodes 1 and 4 aren't connected, but perhaps node 4 could gain information about node 1 if node 5 shares that. Right? That requires node 5 to kind of locally store this information in its state. And what this looks like now is a dynamic controller. So my controller has its own state space realization. And the matrices that describe this state space realization have a sparsity pattern. Okay. So now we've talked about locality in this more complex setting. Let's look at the resulting controller design problem. So this is my standard framework for robust and optimal control. I have some exogenous disturbance or noise coming in and some measure of performance I want to optimize. I can write the closed loop map from disturbance to measure of performance in terms of my plant and my controller. And remember, my controller I can realize with some state space realization. And my goal is to minimize some measure of this performance objective. Key challenges here are that my control computation must be distributed across these local computing units, each of which has access to a limited subset of system information. And this leads to a constrained optimization problem. So rather than just minimizing this objective, I need to constrain the matrices in my state space realization of my controller to have some sparsity pattern. And this becomes quite complex because remember, my map from disturbance to performance measure is already non-convex in K. And now I'm adding this really complex constraint. So I have a non-convex optimization problem. This leads to one of the key challenges for scalable controller design. So a lot of existing work has leveraged convex restrictions of this problem using clever factorizations of the controller. So for instance, if I can write my controller as the product of M, a dynamical system, and N inverse, where N is also a dynamical system, I can implement my controller via this block diagram, where G is another arbitrary dynamical system. One specific example of a convex restriction like this is system level synthesis, which I know folks here are working on. And the nice thing about this is that if I choose these factorizations in a clever way, such that my performance objective is actually affine in these factors, and the structure of M and N implies the structure of my controller K, then I essentially have a convex restriction of this problem. So that's really nice. And recently my group has been looking at extending this to PDE dynamics. I'm going to rush through this because I'm out of time. But we specifically looked at the diffusion equation or heat equation and looked at a quadratic cost. And our theorem shows that this same factorization approach does hold for PDE dynamics. I'll just acknowledge that similar work has recently come out of Caltech where they looked at discretizations of PDEs over finite time horizons. So the difference here is that we didn't make those assumptions. We're looking at the full PDE over an infinite time horizon. So essentially I can do the same convex restriction if I want. So I can break my controller up into these two blocks, design both of these independently, and recover a structured controller. In infinite dimensions, though, I do have some kind of nasty technical assumptions, but they seem to be not so bad, even though they look ugly. You can view our paper if you want. And what's fun about this approach without any approximations about finite time horizon or discretization is that we can find these optimal blocks analytically. And so in infinite dimensions, these are both basically PDEs. And so what I'm plotting here is kind of like slices of the Green's function of these PDEs. And what's great is we can now get an equivalent convex optimization problem. This is a restriction of the problem I might want to solve. And we can think about different constraint sets that characterize locality of my controller, even in this infinite dimensional setting. I kind of rushed through that because I'm out of time, but we do have a paper on archive and I'm happy to chat on offline. But I'd like to conclude before we're completely out of time. And once again, thank my amazing students and my collaborators at CU. And I'd be happy to take any questions now, or if you'd like to chat offline, my email's at the bottom. Thanks.
We have time for a few questions.
Okay.
So, this last part of your talk, where you're looking at basically something kind of like system level synthesis.
Yes, exactly like this. Yes.
For PDEs. Let's say when you say that you still have a convex optimization, that it's convex over an infinite dimensional space because it's a PDE.
Yes.
So don't you kind of have to discretize anyway?
Yes.
So the advantage is really just that you get the analytical solutions that you want, but ultimately, if you wanted to implement it, you're back to discretization, just like
Yeah. So in practice, you do have to discretize that problem to solve it, unless I don't know. Probably in very special cases, you could get some nice results. Maybe using like a joint variable method. But I think more our goal is to gain insight from analytical solutions in really simple settings, and then use that to interpret numerical finite dimensional approximations in more complex settings.
Okay.
Yeah.
I'm still thinking about this like fully decentralized LQR solution. So it's kind of, I think, obvious that if your dynamics is totally decoupled, then you will get the diagonal K. Like if I have this fully decoupled thing and maybe my first off diagonal has some parameters, is it easy to characterize when I would get this decoupling? Like linear finite dimensional system. Really not diagonal. And is it or because like you have very few parameters in your setting, like you have like 2 parameters in Q, 1 R, then C, I guess.
And actually if you use something like the Buckingham Pi theorem to non-dimensionalize your system, you really actually only have 2 parameters that you can tune. So I guess the underlying dynamics when the controller is completely decentralized are still coupled. And I really don't have a physical explanation. We spent a long time trying to understand it and we really just don't. I think the only thing we can kind of say is like your dynamics are coupled, right? So in some sense, like you do know what, like you feel what's happening next to you, even if you don't grab the measurement because you're coupled through the open loop dynamics. But Yeah,
Maybe even the simpler question, I have a
yeah,
two-dimensional system.
sure.
And two parameters that are the off-diagonal ones, and I know
Yeah.
the diagonals.
Yeah.
Is it easy to characterize when I will get diagonal K? That's the simplest thing I
Oh.
think of, or just.
That's a good question. We haven't thought about that, but that is a good question, right? You can just say like, write out your Riccati equation for a general 2x2 A, Q, and R,
Mhm.
and one is the solution diagonal. Yeah, that's a good question. I haven't thought about that.
All right, well, in the interest of time, I think we ought to thank Emily again. I'm sure she'll take questions.
Did I stop the recording?
Oh, there, you got to check the chat. Doesn't include.
Okay.
But I was like, oh, no, they just put on your off.
I don't know.
I
But I
would say, yeah, I mean, especially, yeah, you know that there is an, yeah, we can stop with it, no problem. But yeah, lovely.